According to the Health Resources and Services Administration, more than 106,000 people are waiting for an organ transplant. Each day, 17 of those people will die, waiting and praying for a call that would save their lives. In 2020, of the more than 106,000 transplants that were needed, only 39,000 were received. Demand for tissues and organs is increasing every year, but the organ supply can't meet this demand. To overcome this problem, tissue engineering has emerged, the goal of which is to restore, maintain, and improve tissue and organ functions. Tissue engineering relies on important factors, which are the right cells to do the job, the right environment, such as scaffold to support the cells, the right biomolecules like growth factors to make those cells healthy and productive, and physical and mechanical forces to influence the development of the cells. Now the question is, how can we make a 3D organ or tissue? Just stack up cells? No, that's not going to work. Then what's the answer? The answer is scaffold. Cells can attach to the scaffold structure, forming 3D construction. The main requirement for a tissue engineering scaffold is biocompatibility to avoid inhibition of cell growth. The scaffold must also be fabricated into a 3D porous structure for tissue formation, along with the ability to transport nutrients and wastes. To make a new tissue, patient cells will be cultured in 2D, and once we have enough cells, harvest the cells and then seed them on a 3D scaffold. So, culture the cells within the scaffold, and when tissue grows, transplant it into the patient's body. This reduces the chance of immune rejection. Now we know that scaffold is important for 3D tissue engineering. How can we design scaffold? Simply, we have to mimic natural scaffolds. But wait, how does the natural scaffold look like? Let's take a look inside of a human's body. There are cells, blood vessels, and natural scaffold materials called extracellular matrix or ECM. In fact, the ECM of the human body is a nanofiber gel network composed of several structural proteins. In nanofiber scaffold, cells can attach to multiple fibers so they can stretch and be tightly held by the scaffold. The cells elongate and actively migrate in microfiber scaffold. Now we know what natural scaffold looks like. Let's mimic it. But how? Here comes the role of nanotechnology, where it's being employed for the development of these scaffolds at the requisite nanoscale. Nanostructures can mimic tissue-specific bioenvironments by designing constructs with particular biochemical, mechanical, and electrical properties. Therefore, tissue can be engineered by employing these nanostructures for enhanced cell adhesion, growth, and differentiation. The most commonly used method to fabricate the nanofibers is by electrospinning, which is a nanotechnology. Electrospinning is one method to produce nanofiber structure. When a high voltage is applied to a liquid droplet, the body of the liquid becomes charged and electrostatic repulsion counteracts the surface tension and droplet is stretched. As the charged liquid jet rises in flight, the jet stream begins to bend as the charge migrates to the surface. The jet is then elongated by a whipping process caused by electrostatic repulsion. So to conclude, tissue engineering requires a porous scaffold that will serve as both substrate and support for tissue growth. Using nanotechnology, nanostructures are developed for use as tissue engineering scaffolds. To better understand the relationship between nanotechnology and tissue engineering, I attached a paper that presents a review on areas of research in nanotechnology with potential implications in bone regeneration or tissue engineering. Have a look at it if you want to learn more.